This is a short video about Chapter 3 of Stein's number theory book, and this is all about public key cryptography. And the main thing we'll talk about in this chapter is it builds up to the idea of the RSA encryption system. Before we get into any of that though, and even before we start reading through the book here, there are two E words that we're going to encounter in this section, which sometimes people might think are synonymous, but they're not. The idea of encoding versus encryption. So these are two very different E words. So encoding, to give you an example, that's when, and maybe also too, what am I pulling from? I am just looking somewhere here. So encoding is a method where I take data and I transform it from maybe one thing to another. So for example, I want to transform, say, letters to numbers somehow. That's an example of encoding. Encryption, on the other hand, is kind of how do I lock that? How do I try to make that secret in some way? So to give you an example here, encoding would be taking something like the string of letters A, B, C and turning those into, if I just think about associating the letter with its place in the alphabet, maybe I encode that as 1, 2, 3. So that's encoding. Encryption is how do I take 1, 2, 3 now? How do I do something to it, some kind of an encryption scheme, in order to change it to some crazy number, and there's some kind of a pattern to how I change it to this number that theoretically only I know. So that's the idea of encryption. How do we take the thing we've encoded and make it secret? So that's the big difference between these two E words. In this first video, we won't really get into the methods of encoding. We'll just look at kind of some playful examples about what encryption is. Okay, now we know the difference between these E words, encoding and encryption. And a lot of this stuff, the ideas really took off in the 70s, and that's when we kind of see the power of number theory for, how do we shape modern communication? How do we make sure that stuff is secret when it needs to be? And so to start us off here, we'll look at kind of a fun example that the author poses. And he draws from this old 90s TV show, La Femme Nikita. Maybe you've seen it. And the idea of that show was this woman, Nikita, is some kind of a spy. She works for some shady anti-terrorist organization that's called Section 1. And she's also got a fellow agent for Michael. And she's got a buddy named Walter. But everybody else in Section 1, it's shady. And everybody else in there is not to be trusted. So here's a synopsis of one episode of the show that the author provides. And so Michael and Nikita, they secretly need to be able to rendezvous with each other to talk about something. And they have an idea for how they're going to encrypt messages to each other, say. But one of the hackers at the evil Section 1 comes across some of these encrypted messages between Michael and Nikita. And so in that case, this hacker has these encrypted messages. Does he know how to decrypt them? And in this case, I'll show you a way of, yes, he will be able to decrypt them with the example that we'll look at below. So that's the idea though. I've got some encrypted message. Could I decrypt it? And then also, if I've got a message, how do I encrypt it? Because the idea is, I'm going to send that message out over public channels. Everybody's going to be able to read, if I scroll back up here, everybody's going to be able to see this number here. How do I make sure that what that actually is secret for, it's secret for 1, 2, 3. How do I make sure that that's sturdy? How do I make sure that's secure? Okay, and we'll look at some concrete examples here too. If you're wondering too, these are Professors Diffie and Hellman, and they are really kind of the fathers of the idea for how some modern encryption systems work. And so what we'll look at is just maybe a toy kind of crypto system. It's not a very good one, as you'll see, but an example of what a Diffie-Hellman key exchange sort of looks like. And so here's the idea. So Nikita, say, has a phone, and she's going to call Michael, and this is what they're going to do. The following is what they're going to do. So she's on the phone, right? And so everything, you got to think about everything they're saying to each other on the phone, they could be being listened to, say. So together, Nikita and Michael choose some big prime number P and some number G that's between 1 and P. So what I'm saying to you so far is Nikita and Michael pick P and G, but anybody listening to that conversation also knows P and G. So P and G are public information. Now, Nikita is going to secretly choose N. She's not going to tell anybody. She's not telling Michael N over the phone. It's in her head. So that's secret. So Nikita's N is secret. Michael is going to do the same. He's going to secretly choose some integer m. This m is just in Michael's head. He did not tell anybody. He does not say m over the phone. Here's what they do tell each other over the phone. Nikita tells Michael what the product n times g is, her secret n times that public g, mod p. And so here's kind of, right here, I'd like to say, the idea for, couldn't anybody just compute that? It kind of depends. So one of the ideas for the system is, even if everybody knows g and n, even if everybody knows g and p, those are the letters I've highlighted, sometimes it can be really hard to recover what n is. It's not just some simple equation we can solve. So in general, that could be hard to solve, and that's kind of the big idea behind modern cryptography. Similarly, Michael, over the phone, is going to tell Nikita n times g and what it reduces to mod p. And again, everybody knows this g and this p again, but only Michael knows what this m is. And so the point then is, how would Nikita figure out what Michael's m is from this? If she knows what m times g is, mod p, could she figure out what m is? And the idea is she could just compute the number n times m times g, and that's called s, mod p. So they can use that as their secret key. And so notice too, this s here, theoretically how the s should work is only Nikita and Michael should be able to figure out what s is, because it consists of, s consists of n, which only Nikita knows, times n times g. And or you could look at it from the perspective of, it consists of m, which only Michael knows, times n times g, which, Nikita tells Michael that. So theoretically, only Nikita and Michael have enough information to put this together. At least that's what you might think. So let's do kind of a nice example with some concrete numbers to kind of show you how this works, and to show you about why this might be a bad crypto system too. So here's a simple example. Let's take p to be 97 and g equals 5. So remember, right now this is public. Everybody knows that. And I'll stop highlighting too. N equals 31. This is secret. M equals 35 is secret. N times g is 58 mod 57. That's public. M times g is also public. But theoretically, this should be secret. So I'll put quotations around secret. But in fact here, this is actually a bad way to try to encrypt things. So in other words, it's actually pretty easy to figure this out given some of this other information up here, and I'll show you why. But just to recap so far, everybody knows these, and that's what I've labeled as public so far. So what would I like to be able to do? I would like to be able to figure out, say, if I'm listening on the phone to their conversation, if I can figure out, say, Nikita's secret key, then I can figure out any of their communications that they're trying to have in secret. Similarly, I could also look at this from the perspective of, maybe I could figure out Michael's secret key. Theoretically, I could figure out both of them in this example. I'm just going to show you how could I, the hacker, say, figure out what Nikita's secret key is. And so the idea here is, what do I know? I know that 1 is less than g is less than p. P is prime, so g definitely doesn't divide p at all, and they don't share any factors since, well, g is smaller than p too. So that tells me that the GCD of g and p are equal to 1. And remember, what that tells me is that there exists integers a and b such that a times g plus b times p is equal to 1. So let's go ahead and just figure out what these integers are. And you notice the book points us to, if we wanted to do this by hand, algorithm 2.3.7. I'll just remind you how to do that in Sage really quickly. So remember, you type in xgcd, and I'll tell it my numbers were, I think, 5 and 97, if I remember right. Maybe I should check that just to be sure. Yeah, 5 and 97. Great. Make sure you put them in that order. And so I get the GCD is 1, A is 39, and B is -2. So this is 39 times 5 plus -2 times 97 equals 1. So my point now is, what can I do? I'm going to take this equation now, and I'm going to multiply everything through it by, what do I want to know? I want to know what n is. So I would say, let's multiply it all by n. And I want you to notice what happens when I, in the next step, reduce everything mod p. When you reduce all this stuff mod p, this term has a P in it. It's not there. So what do I have then? I have, that's, to recap down here, I know that A and G, that's this right here, I'm just not writing nag like I did right there, is equivalent to N mod P. So in other words, if I could figure out what A times N times G is, then I could tell you what N is mod P as well. And how can I know this? Why is that any easier? Well, it's because everybody knows N times G is 58, and we just figured out that A is 39. So this should be equal to 39 times 58. So we have just figured out what Nikita's secret key is. So that's not good for Nikita. We kind of hacked her system here. And so what we'll look at is what are ways that we can make this stronger so that an attack like that is not possible.